Welcome to this explainer. Today, we're going to explore exactly how engineers predict the unpredictable, totally chaotic world of fluids. Whether it's the air rushing over an airplane wing, water pumping through a city's infrastructure, or even the heat swirling right now inside your computer case, fluids are constantly in motion, and honestly, their behavior is notoriously complex. So, we're going to unpack the fascinating journey of computational fluid dynamics, or CFD for short, taking it all the way from foundational physical laws right up to the cutting-edge digital realities used in modern engineering. Let's get started. So how do engineers predict the unpredictable? Think about it. Fluids are absolutely everywhere, yet their chaotic nature makes them incredibly tough to model. If you've ever watched smoke rise from a campfire, you know what I mean. It goes straight up for a bit and then suddenly breaks into these swirling, entirely random eddies. You're seeing firsthand just how complicated fluid behavior can be. So how do we mathematically predict something that seems so inherently random? Well, to do that, we have to start at the very beginning. Before we simulate anything, we have to agree on what we're actually looking at. By definition, a fluid, and that means either a liquid or a gas, is a substance that moves and deforms continuously as a result of an applied shear stress. Think about a solid block of steel. If you push it, it bends or maybe it breaks. But a fluid? It just keeps on deforming and flowing for as long as you're applying that force. And that continuous, non-stop deformation is exactly what makes modeling them such a massive challenge. Okay, here's our game plan for today. 1. The fluid continuum. 2. 3 laws of mechanics. 3. The substantial derivative. 4. Meshing and boundary layers. 5. Modeling heat transfer. And finally, 6. The digital wind tunnel. Section 1. The fluid continuum. Modeling fluids as continuous matter. In reality, a fluid is just a giant, completely chaotic mosh pit of molecules bouncing off one another. But if we actually tried to calculate the collision of every single molecule in, say, a hurricane, even our most powerful supercomputers would immediately crash. There's just no way. So instead, we assume a continuum. Basically, as long as the volume of fluid we're looking at is large enough, specifically anything larger than about 10 to the negative 9th cubic millimeters, the random molecular variations just average out. Things like density, pressure, and temperature become smooth, continuous point functions. And this is a real game changer, because treating the fluid as continuous matter finally allows us to use differential calculus to solve real-world problems. Moving on to Section 2, 3 laws of mechanics, the absolute governing rules of fluid dynamics. You see, all of computational fluid dynamics is fundamentally anchored to 3 completely non-negotiable physical laws. First, mass is conserved. Simply put, what goes in must come out, which gives us our continuity equation. Second, Newton's second law, force equals mass times acceleration. In the fluid worlds, this becomes our momentum equations, which detail how pressure, viscous forces, and gravity push the fluid around. And third, energy is conserved, which is the first law of thermodynamics, giving us our energy equation. Every single complex CFD simulation you will ever run is, at its core, just a massive mathematical machine making sure these 3 rules are never, ever broken. Section 3, the substantial derivative, how we translate this physics into math. Okay, I love this analogy. Imagine you're walking into a cold cave. The temperature drops simply because you are physically moving from a warm area into a cold area. That's known as the convective derivative. But exactly as you step inside, your friend hits you with a snowball. That causes a sudden, momentary drop in temperature right where you're standing. That is the local derivative. The substantial derivative is what brings this all together. It brilliantly combines both effects, calculating the time rate of change of a property as you, or a tiny fluid element, move through the flow field. Now for Section 4, meshing and boundary layers, chopping the continuum into computable pieces. To actually compute this on a computer, we divide the fluid volume into a discrete mesh, allowing the software to calculate the temperature, velocity, and pressure inside every single cell. But here's the catch. We have to be incredibly careful near solid walls. Fluid tends to stick to walls, creating a steep gradient known as a boundary layer. To really understand why this matters, let's think about a golf ball. A golf ball has dimples that act as deliberate surface roughness. When the ball flies at a Reynolds number of about 10 to the 5th, which is right in the sweet spot, those dimples trigger an early transition from a smooth laminar boundary layer to a turbulent one. And to capture this critical boundary layer behavior in a simulation, we need highly precise mesh inflation layers, using tools to perfectly control the growth rate and sizing. Splitting these mesh prisms conformally allows us to refine the boundary layer without having to drastically alter the entire rest of the mesh. Going from 3 basic layers to 9 highly refined layers, exactly where we need the most, lets us mathematically capture some incredible physics. Let's go back to our golf ball. A turbulent boundary layer contains a lot more momentum, making it super resistant to adverse pressure gradients. Basically, it clings to the surface much more effectively. For a perfectly smooth ball, the airflow separates at about 80 degrees, creating a massive wake. But with the turbulent flow from dimples, separation is delayed all the way to about 120 degrees. We absolutely need this highly split, dense prism mesh right against the wall to accurately simulate that delayed separation. Now, notice how peel layers act as a smooth buffer zone here. They bridge that highly detailed boundary mesh to the larger core volume mesh, which ensures mathematical stability. Why is this so crucial? Well, for blunt bodies like our golf ball, pressure drag or form drag is the dominant force. On a cylinder, for example, it accounts for like 97% of the total drag. It's caused by the difference between high pressure at the front and the low pressure wake at the rear. By delaying separation and narrowing the wake, dimples drastically reduce this pressure imbalance. It drops the ball's total drag coefficient from about 0.5 all the way down to 0.2. That is a 60% reduction in drag. Add in the spin, which creates a side force known as the Magnus effect for extra lift, and that is exactly how a golf ball can fly so incredibly far. All right, Section 5, Modeling Heat Transfer, Conduction, Convection, and Radiation. By activating the energy models in our software, the simulation can simultaneously solve for conduction in solid walls and convection within the fluid itself. This is what's known as conjugate heat transfer. Imagine a hot object placed in a cooler stream of fluid. Conduction pulls the heat through the solid object, while convection transports that heat away as the fluid rushes past. And if things get hot enough, we even have to calculate radiation, traveling as electromagnetic waves. The really cool part is that modern software couples these zones automatically, ensuring that the heat leaving the solid surface perfectly matches the heat entering the fluid. Here is a practical insider tip for you. Always check your energy fluxes to ensure your simulation has actually achieved a balanced, converged state. Look, it's one thing for a simulation to just say it's finished running, but you have to verify the physics yourself. If the total heat entering your simulated system doesn't essentially equal the total heat leaving it, your net value isn't zero. And if it's not zero, that means your digital reality hasn't obeyed the first law of thermodynamics yet. So always check the energy balance. And finally, Section 6, the digital wind tunnel, the third approach to fluid dynamics. Thanks to CFD, we no longer have to rely solely on chalkboards or wildly expensive physical wind tunnels. For centuries, engineers really only had 2 approaches. You either sat at a desk solving idealized mass, or you built a physical model and tested it in the real world. CFD is the revolutionary third approach. It gives us a digital laboratory where we can rapidly iterate designs, visualize totally invisible thermal fields, and pinpoint the exact pressure drag in a golf ball's wake. It lets us deeply understand the core physics before a single piece of metal is cut or a prototype is ever manufactured. Now that we have the computational power and the tools to visualize the invisible forces of nature, I want to leave you with this thought. What incredible innovations will you design next? By understanding the fluid continuum, respecting the absolute laws of mechanics, and mastering the digital meshes that bring all these equations to life, the barrier to predicting the unpredictable has literally never been lower. Thank you so much for joining me on this explainer. Keep questioning, keep learning, and I'll catch you in the next one.